Welcome to Structural Engineering Online. We are dedicated to provide teaching and learning support through video lectures. Please subscribe to our channel if you have not yet subscribed. Thank you very much. In this lecture, we will learn how to determine the support reactions of a compound beam and draw SFD and BMD for this beam. If you look at this figure which is given here, there is one roller support at A and there is fixed support at F. But if you look at this point D here, there is an internal pin. That means the two beams are connected together. You can say ABCD is one beam, and then from DEF, this is another beam. These two beams are connected with the help of this internal pin. That's why it is known as a compound beam. What is happening at this internal pin? As you know that a pin will have two reactions. So here we have to draw the free body diagram for each of the component of this compound beam, and then we will be solving it. So first of all, we have to draw the free body diagram for each component of this beam. So we first take here, this is our support A, will have one reaction because it is a roller. Then we have uniform load 2 kilonewton per meter. After that we have this 3 kilonewton load. And then what is happening at D? At D you will have two reactions, one vertical and one horizontal. We don't know the value of these reactions, but there will be dy, and here you have ay, the reaction, and this will be dx. There will be two reactions. Now what is happening at this pin? Because this pin is part of both the components DEF and ABCD, so whatever it will take from this left hand side beam, it will transfer it to DEF in the opposite direction. So in that case, you can say if dx is left hand, then it will transfer dx in the right hand direction there, and if dy is upward here, it will transfer dy in the downward direction for this second part, which is your D, E, and here we have F. Now at F, as you know that there is fixed support, so fixed support will have three reactions, one vertical, one horizontal, and one moment. So we have moment at F, and there will be a horizontal force Fx, and Fy will be vertical, and there is a load of 2 kilonewton here at point E. The distances are same as 3 here and 3 for this part, and here also you have these distances, 4 meter, this is 2 meter, and this is 2 meter. Now we look at these components individually. If you look at A, B, C, D, on this beam you find AY is unknown, DY is unknown, DX is unknown. So in that case, we have here three unknowns, which you can easily calculate with the help of equilibrium equations: sigma fx equal to 0, sigma phi equal to 0, and sigma m equal to 0. So there will be no problem, you can easily find. But if you look here at the second component, which is DEF, here you have two reactions, one horizontal, one vertical at point D, and three reactions, which is Fy, Fx, and Mf. So total 5 reactions are there for this beam DEF. So if you try to solve it individually, you will not able to, because 5 reactions and you will get only 3 equations of equilibrium, because this is one single rigid body. As you know that every rigid body gives 3 equations of equilibrium. If you are not familiar with this, you can see our previous lectures on the topic where you can learn how to find the degree of indeterminacy of the beams, frames, and trusses. So now if you look at this A, B, C, D, E, if you can get the value of dy and dx from here, then we can apply the values in the equal and opposite direction at point D. Then this DEF will also have just three unknowns, which will be Fy, Fx and Mf. So this way we have to first identify which part of our compound beam is determinate. So we find that this is our determinate part. So first we will start from here, and then we will calculate the reactions for this support. So you can say that we will work for, this is our first part, this is second part. So segment A, B, C, D. Now we are dealing with it. So we can calculate sigma Fx equal to 0. And if you look here, in horizontal direction for this part, there is only dx, which is shown in the left hand direction. So we can say minus dx, and there is no horizontal force. So for equilibrium, this will be equal to 0. And this says that your dx is 0. Then we write the equilibrium equation in y direction, that is sigma Fy is equal to 0. And in that case, you can say that plus Ay, then minus 2 into 4 minus here, yes, this is minus 3 kilonewton, which is acting downwards. So minus 3 and then plus dy equal to 0. So from here we can get the value of Ay plus dy. So Ay plus dy is equal to 8 plus 3, 11. This is our equation number 1. So once we get this, now we can go to the next equation, that is sigma m about A equal to 0. So we take the moment of all the forces about point A, and this will give you dy into 8, moment of dy about point A. So dy is at a distance of 8 meter, and this will give you anti-clockwise moment. That's why we have taken it with plus sign, that is our sign convention. Then minus moment of 3 kilonewtons, because it will give you clockwise moment. So it will try to rotate like this. So it will be 3 into 6. So minus 3 into 6, the moment of 3 kilonewton force. Then we have 2 kilonewton per meter UDL, and this UDL will be acting at the center of this length. That means its center will be at a distance of 2 meter from A. So this load will also give you anti-clockwise moment. So minus 2 into 4 into the distance 2, like this. And this whole thing will be equal to 0. There is no other force remaining. Dx will not give any moment because the distance of dx from point A is 0. So this whole thing we put as 0. So from here you can say that the value of dy is, when we simplify this, we get dy equal to, this will be 16 plus 18 divided by 8, and you will get this value as 34 by 8, or you can say 4.25, and this is positive. This positive sign here indicates that our assumed direction of Ay and dy, whatever we have assumed, because in the beginning we were not knowing the direction of Ay and dy, our reactions in vertical direction, similarly the reactions in horizontal direction, we were not aware of this direction. So that's why I advise you that you always take the positive direction as your assumption, and at the end if you get minus sign, that means your reaction is actually in the opposite sense what you have taken. So now here we are getting dy as positive, that means dy what we assumed is correct, it is acting in the upward direction. Now we apply this, we substitute this value of dy in our equation, and we can get the value of Ay, which will be 11 minus dy. So we get this value here as 11 minus 4.25, and this is equal to 6.75. So this will be positive. That's why AY is also positive, which is correct. We don't have to reverse the direction. So 6.75, this is also upward, and this one is also upward. Okay, this part we have solved. Now we go to the second component, which is your DEF. And what we will do now, as we got the value of dy, okay, dx is 0, so there is no problem with dx. Otherwise we get the value of dx in the left hand direction, then we will apply this dx in the right hand direction at point D for DEF. So this internal pin is just transferring the reactions in the opposite direction on the other segment which is connected. So now we can apply this force dy in the opposite direction of dy, which we have calculated. So here is our second part, which is like this. So here we have dy, which is 4.25. Now you have got the value of dy. Dx is equal to 0, so there is no need to apply dx. And then we have a force of 2 kilonewton. This is 2 kilonewton force, which is given at a distance of 3 meters from here. And then we have this. Okay, so this is Fx, this is Fy, and this is Mf. This is your point D, and this is E. This distance is also 3. So now our job is to find the value of Fx, Fy, Mf. These are the 3 unknowns, and which you can easily calculate, and very quickly you can say, because sigma Fx, sum of all the forces in x direction, will be equal to 0, and that gives you, there is only one horizontal force, no other force is there, so this force Fx will be equal to 0. Force at this support F in x direction. Then we write sigma Fy equal to 0, and that gives you that Fy is upward, so plus Fy minus 4.25, because it's acting in the downward direction, minus 2 equal to 0, and this gives the value of Fy equal to how much? We get the value of Fy equal to 4.25 minus 2 is 6.25. So we have got the value of this force Fy as 6.25. Very simple. Now we get the value of Mf. So apply the third equation, sigma m about f equal to 0, and what do we get from here? Take the moment of all the forces here. So the force 4.25 will give you anti-clockwise, so anti-clockwise will be positive, so 4.25 into the distance from point F, which is 6, and then 2 into the distance of this force from point F, which is here 3, and then the moment at this support F, that is Mf, which is acting in the clockwise direction. And in fact this Mf was assumed by us, we were not knowing the direction of Mf also, so we assumed this direction, and so according to our direction assumed, we will put this as Mf according to our assumed direction. Clockwise we have taken, right? So minus Mf, and that is, there is no other moment, equal to 0. So from here we can get the value of Mf, which will be 4.25 into 6, and then 2 into 3. So this will be 6 plus 25.5, and that is 31.5 kilonewton meter. Now we have got the reactions. So all the reactions are known, and now you are in a position to draw the shear force diagram and bending moment diagram for these two components of your compound beam. And this is very simple part. Here in the case of A, B, C, D, you have these point load and uniform load, and this D, E, F is just like a cantilever with 2 point loads, and you have already learned how to calculate these things. Okay, we will also provide the link for developing shear force and bending moment diagram. You can learn from that link. We will give the link in the description. Okay, now we come to this first part, which is A, B, C, D, E, and we will draw the shear force diagram and bending moment diagram for this component. Okay, so we draw the diagram here. This is your A, B, C, D. Here is the force A, which is 6.75, and then you have UDL of 2 kilonewton per meter. The length is 4 meter. Then you have a load of 2 kilonewton, and then here is the reaction 4.25, and these things 2. So this is your beam, and now we will draw the shear force and bending moment diagram for this beam. We will take these reference lines, okay, to plot the values. Yeah, okay, here is the axis X. Now we will substitute the values of these components here. So shear force, if we see here, 6.75 at your point A, which will go up 6.75, right? And after that, if you see, this is okay, your point A, this is B, this is C, and this is D. So shear force at A is plus 6.75. Now if we calculate shear force at B, you can simply see the values of these forces on the left hand side of point B. So 6.75 is upward, okay, 6.75. Then there is a uniform load of 2 kilonewton per meter for a length of 4 meter, and that load is acting downward, so with minus sign, 2 into 4, and this value will be simplified to get a value of 1.25 with minus sign, so it is equal to minus 1.25. So shear force at B is minus 1.25, at A it is positive, and you know that the uniformly distributed load will give you a shear force diagram that will be a sloping line. It will not be a constant. When there is point load, there will be constant line, means that will be horizontal, means parallel to x-axis, but in the case of UDL, it will be inclined line. So here we'll just join these 2 points, 1.25 here and 6.75. So we join by this straight line. Okay, then after this point we come to C, FC. In the case of FC, it will be same, because we will not consider this load at point C. Just before point C, if you see, the values will be same, 6.75 minus 2 into 4, and it will be same, minus 1.25. So it will remain constant up to point C. And then we come to this point D, and that is very simple for you, that you can say it will be also calculated from the right hand side. So that value will be 4.25, or you can also calculate from left hand side. So 2 kilonewton is down at point C, we take here, and this will complete. So the value is 4.25 here, and this is 6.75. This is positive and this is negative. So this completes your SFD shear force diagram, right? So FD is minus 4.25. Now we go to the bending moment diagram for this beam, and for that, okay, we will continue these reference lines here. Okay, we draw this. So this is your reference line. Then you know that bending moment at the hinge support or roller support, which are at A, it will be always 0. You can easily calculate. On the left hand side of A there is no force, and at A is just a force 6.75. Even if you take the moment of 6.75 at A, it will give you 0. So we can say at A bending moment 0. Similarly at D the bending moment equal to 0. There is no force on the right hand side of D. So at A and D we know the values of this bending moment. Now we can calculate moment at B. Okay, moment at B. Now look at the left hand side of B. There is a force which is point load 6.75 here. So we will take the moment of this, and there is uniform load of 2 kN per meter for a length of 4 meters. So these two will give you the value of bending moment at B, and we will use the same sign convention, that sagging and hogging. Sagging moment will be taken as positive and hogging will be taken as negative. So very simple convention is that all vertically upward forces will give you the sagging moment, and all vertically downward forces will give you the hogging moment. So here we can simply use this 6.75 into 4, which will be sagging, and this 2 kN per meter, which is acting downward, will give you hogging moment. So we can say here minus 2 into 4 into the distance 2 from the center of this UDL to point B. So this way we get the value of MB equal to, so moment at B is how much? Let us get this value. Moment at B we get 6.75 into 4 minus 2 into 4 into 2. Okay, so this is equal to 11 kilonewton meter. So now we have got the value, and you know that whenever there is uniform load, there will be bending moment diagram having the shape of a parabola. Now you have to decide how that parabola should be driven, whether it should be concave parabola or convex parabola. So here one thing is very clear, that the value at point B 11 kilonewton meter. So we have this value, suppose this is 11 here. Now look at the point where the shear force is 0. Here is the point which is giving you 0 shear force. So we know the relationship between maximum bending moment and 0 shear force. The point at which shear force is 0, the bending moment will be maximum. So if you know that point at which shear force is 0, you can say that there will be the peak value of your bending moment parabola. So here you will have some value somewhere here, the peak. So parabola will go like this, it will reach at the highest point and then it will come back here. So that value you have to calculate what is this maximum. But here at point B you have the value 11 kilonewton meter. So this I will write here as 11. Okay, so this is 1.25. Now we will calculate the value of bending moment at point C, which you can calculate from right hand side also, which will be just 4.25 into 2. So bending moment at C will be equal to 4.25 into 2, and that value will be equal to 8.5. and of course it will be straight line. And if you want to see why there is straight line, why there is parabola, you can see the link which we are going to provide in the description. That will help you to understand the nature of curve for the bending moment diagram and shear force diagram. So now we'll plot here this value 8.5 and this is the value. Now you have to find the value of maximum bending moment, which you will calculate with the help of this point, which is having 0 shear force. And you can easily calculate this point where the shear force is 0 by using the concept of similar triangles. So if you look at this positive triangle and this negative triangle here, so these are the two triangles of shear force which we will be using to find the value of x. So we can say that x upon 6.75, the sides will be proportional, so ratio of the sides will be equal from these two. So x upon 6.75 will be equal to 4 minus x upon 1.25. So from here, when we simplify, we get the value of x as 3.5. This is value of x. That means at x equal to 3.5 from point A, you will get maximum value of bending moment. Now we can easily calculate what will be the maximum value of bending moment, m max. So we calculate at x is equal to 3.5. So now here at x equal to 3.5, the moment of reaction at A and the moment of uniform load. So 6.75 into 3.5, then minus for UDL. UDL extending downward 2 kilonewton per meter. So for a length of 3.5 meters, so 2 into 3.5 into half of 3.5. Okay, and when we calculate this value, we get this value as 11.375 kilonewton meter. So this way now we have got the value of maximum bending moment, 11.375. You can complete now. Okay, this is 11.375. So this is all positive. Okay, now bending moment diagram is also complete for the segment A, B, C, D. Now we'll go to the second part, which is D, E, F. So in the similar way, we can easily draw the bending moment and shear force diagram for this D, E, F. Okay, D has a load of 4.25. E has a load of 2 kilonewton, and at F there is a reaction which is 6.25, and there is a support moment of 31.5. So this is your D, E and F. So we'll draw the reference lines here also in the similar way, and you know very well that this is just like a cantilever with point loads. So we can quickly draw this diagram here. Okay, this is the reference line. Then shear force in the similar way, 4.25 at D, so it will be downward. Then it will be constant up to E. There is nothing, no load from D to E, so it will remain constant. If you calculate at any point, either here, just look on the left hand side and see the direction of the forces. So because shear force is the algebraic sum of all the vertical forces, right, on the left hand side of the section. If you want to calculate from right hand side, then you will calculate the forces on the right hand side. Okay, so here we have this value 4.25. Now when we come to point E is giving you another load of 2, so it will go again down to here, and then again it will be constant, and that comes out to be 6.25, and that completes your shear force diagram. Okay, it's very easy. And then we go to the diagram for bending moment. Draw these reference lines. Okay, at point D, what you will get? You will get the value of bending moment 0 at the free end of cantilever. There is no moment, so simply, and if you look at the same, because downward forces, as I told you, will give you the hogging moment, and hogging moments, so 0 here, this value is 0. Then at point E, we calculate moment at D is equal to 0. Then we calculate moment at E, which will be 4.25 into the distance, which is 3 from D to E. This is 3, here also 3. And the sign for hogging moments, it will be minus. So this value comes out to be minus 12.75. Okay, so it will be a straight line because there is point load and there is no uniformly distributed load. Only in the case of uniform load you will get the parabola. Otherwise, when there is point load, it will be a straight line, that will be a sloping line. So from 0 to 12.75, okay, we get this value, straight line. And then we come to the moment at F. F. Again, you can take the moment of these forces. There is a force of 4.25 at D, and there is a force of 2 kilonewton at E. Both of them will give you a moment, and that should be same as 31.5 if you calculate from the right hand side, because the moment at the support is 31.5. Otherwise, you can check from left and right, you will get the same value of bending moment. So here, okay, we will calculate from the left. So 4.25 with minus sign, 4.25 into how much? 6, because the distance is 6, and then 2 kilonewton has a distance of 3, so minus 2 into 3, and this whole thing will give you a value of minus 31.5, which is same as the value of support moment. That also checks our calculation. So this will also be a straight line, so we will join it by a straight line like this, and that completes the bending moment diagram. BMD right here, the value is 31.5, and here the value is 12.75, this value, and this one is 0. So with this, we come to the end of this question for shear force and bending moment diagram for a compound beam. I hope this lecture has helped you to understand how to solve the problems of compound beam. So in summary, you can say that we have to split that compound beam into 2 segments. If there are 3 segments, you will split it into 3 segments, and then you will solve one by one each segment to calculate the reactions and draw the shear force and bending moment diagram for each segment. The main thing what you have to keep in mind, that you will be transferring the reactions from one side to the other in the opposite direction. That's all. Okay, so I hope this has helped you in learning something new, that is about compound beam. And if you like this video, please share it with your friends so that they can also get the benefit. And please subscribe to our channel so that in future whenever we upload, you will also get the benefit of other lectures. Thank you very much.